In current electricity, next topic is Wheatstone Bridge. The circuit for the Wheatstone Bridge is shown in the figure. Here four resistances P, Q, R, S and is forming a network, and the two terminals A and C across which a battery B is connected, while the other two terminals say B and D, a galvanometer is connected. In balanced condition, that means if Wheatstone Bridge is balanced, in balanced condition, the current in the galvanometer will be 0. Ig will be 0. This implies that voltage or the potential at the terminal B will be equal to potential at the terminal D. And under this balanced condition, the condition for balanced Wheatstone bridge is that P by Q equal to R by S, which we have to prove. This is the condition for Wheatstone bridge to be balanced, and under balanced condition, current in the galvanometer, that means from B to D, will be 0, and we can other ways also said that potential at B and D are equal. Now we have to prove this condition of the balanced Wheatstone bridge. Here we suppose that current I is flowing from the battery and it reaches the junction A, where it divides into the two branches, say I1 through the resistor P and I minus I1 through the resistor R. Where it reaches B, under the balanced condition, when galvanometer current is 0, then there will be no current in the galvanometer, so this whole current I1 will pass through the Q, and similarly this I minus I1 will pass through the S. And now at C they both meets and forms the current I, and this completes the circuit. So this is, we mentioned the current as per the Kirchhoff's first law, that is also known as the junction law. Now using the Kirchhoff's second law, that is the loop law, we write the loop equations for, because there are the two unknowns I and I1, so we require two equations. So we take one of the loop as A B D A, and for this loop we move clockwise and write the equation. Here current I1 is flowing through P, so potential drop across in the direction of current is taken positive as per the convention, because it is in the direction of decreasing potential. Then from B to D there is no drop in the voltage, so it is 0. After this we reach D, and D to A we are moving in opposite direction of the current, so it is minus I1 into R, and it is equal to 0. This is the equation number 1. Similarly we take the another loop, that is B C D B. In this loop again we write the equation and move in clockwise direction, so it is I1, because moving in same direction of current, so it will be taken positive, I1 into Q. This is the voltage drop across Q. Then we reach C. After C we move to the D. Here we are moving in the opposite direction of the current, so it is minus I1 into S. And after that from D to B there is no current in this branch, so finally it is 0. This is the equation number 2. So now rearranging this equation number 1, this is I1P equal to I minus I1 into R, and from second equation I1Q equal to I minus I1 into S. Now dividing the equation number 1 by 2, on dividing we get P by Q, because I1 get cancelled, and similarly on right hand side I minus I1 will also be get cancelled, and it is equal to R by S. And this is the condition for the balanced Wheatstone bridge. And on this principle, a device which uses this principle, it is called the meter bridge, which is used to calculate the resistance of the unknown resistor using the standard resistance. Let's take one question. Here in the given network, we have to find the equivalent resistance between the terminal A and B. This is the terminal A and B. Across this, we have to find the equivalent resistance. If we check the network, this is the network like the Wheatstone bridge. And first we will check if the condition of the Wheatstone bridge is satisfied or not. So condition for balanced Wheatstone bridge is that P by Q equal to R by S. Say this is P, this is Q, this is R, this is S. So we can write 100 by 200 equal to 60 by 120. This implies that 1 by 2 equal to 1 by 2. This means the condition of Wheatstone bridge is satisfied. Hence, terminal C has the same potential at D. That means there is no current in the 15 ohm resistor. So I across the 15 ohm resistor is 0. It means we can ignore this 15 ohm resistance, and now equivalent circuit between A and B is a resistor 100 ohm, which is up to C. After C to B there is a resistance of 200 ohm, and A to D there is a resistance of 60 ohm, and from D to B there is a resistance of 120 ohm. So these two resistances are in series, and in series we directly add the resistances. So it is 100 plus 200, that is equal to 300 ohm. And here these two resistances are also in series. So their resistance will be 60 plus 120, that means 180 ohm. And these two resistances are in parallel. Therefore, between terminal A and B there is an equivalent resistance R, and this R will be equal to the parallel combination of 300 ohm and 200 ohm, or from the parallel combination we know R is equal to R1 by R2 plus oblique R1 plus R2 if R1 and R2 are in parallel. Therefore, we put the values here: 300 into 180 by 300 plus 180. So it is equal to 300 into 180 by 480. We try to cancel out. It is 100, 16, and this is 25. This is 2. This is 9. 225 by 2. That means it is 112.50. Now we take the next question. In the given circuit, we have to find the effective resistance between the terminal A and C. Here, first we check the condition of Wheatstone bridge, if it is satisfied or not. So if we replace the resistance with values P by Q equal to R by S, if P is 10 ohm, Q is 10 ohm, and this is R and this is S, we will find that 10 by 10 is equal to 10 by 20. And this is a false statement. So it means Wheatstone bridge is not satisfied. So we have to use the Kirchhoff's rule to solve this problem. Here, first we draw the current using the Kirchhoff's junction rule. Here current is divided into the junction A in currents I1 and I minus I1. After that, at junction B, this current I1 will divide in two parts, say I2 in the 10 ohm resistors, and this current will be I1 minus I2. And now I minus I1 current will reach here, and from the B, the current I2 will reach here, and in this branch S, current will be I minus I1 plus I2. And at C, there are the two currents which meets, so outgoing current effectively will be I, and it satisfies the junction rule at each and every junction. Now we apply the loop rule, because there are the three variables I1 and I2. So we need three equations to solve these values. Therefore, you choose two loops. Loop number 1, A, B, C, A. Loop number 2, and we will move in clockwise direction, B, C, and this is D, B, C, D, B. So there are the four loops, A, B, D, A, first loop. This is the loop number 1. Similarly, we take loop number 2, that is B, C, D, B. And then third loop, it is the third loop, will move in clockwise direction, and it is A, D, C, A. And now we write the loop equation to write the voltages across a loop. So for the first loop, starting from A, we will get I1 into 10 ohm, because we are moving in direction of current, that means decreasing potential direction. So it will be taken positive, then plus I2, and it is 10 ohm again. And then in third, it is we are moving in the opposite direction of the current, so it is minus I minus I1 into 10, and it is equal to 0. This is the equation number 1, and it can be further simplified. First we writing the equation. So second loop, from starting from B, it will be I1 minus I2 into 10, it will be taken positive because moving in direction of current. Then minus, and current is I minus I1 plus I2, and resistance is 20 ohm. And third one is again taken minus, and current is I2 and resistance is 10 ohm, and it is equal to again 0. This is the equation number 2, and taking the third loop starting from A, it is I minus I1 into 10 because we are moving in the direction of current. Current is moving in this direction. Then we reach to the 20 ohm resistance. Here also same direction of current, so it is plus I minus I1 plus I2 into 20. And after that C2A, there is no resistance, only battery is here, and here in battery we are moving in the increasing direction of potential, so it will be taken negative 10, that is equal to 0. So we get three equations, and now writing this equation on simplification, we will get equation number 1 as I1, this is the 10 I1, and it is minus minus plus 10 I1, or we can simplify by cancelling this 10, so it is I1 plus I2 minus I plus I1 equal to 0. So we can write this equation as 2I1 plus I2 minus I equal to 0. This is equation number 1. Similarly, in second equation, we can also simplify it. Is this 10 will be cancelled by this, and here it is 2. So it will be I1 minus I2. Here it is 2, so it is minus 2I plus 2I1, then again minus 2I2, and here it is simply plus minus I2, and it will be equal to 0. So we can write this is I1 and it is plus 2I1. So it is 3I1, then minus I2, and it is minus 2I2, that is minus 3I2, and it is again minus 1. So it is minus 4I2, and rest is minus 2I equal to 0. So this is equation number 2. Now for this third equation, this 10 will get cancelled, and remaining terms will have I minus I1 plus I minus I1 plus I2, and it is multiplied by 2. So we have to multiply this with 2. So this will be I minus I1 plus 2I minus 2I1 plus 2I2, and remaining here it is minus 1, that is equal to 0. So it will give, if we add I1 minus 2I1, that means it is minus 3I1, and then it is plus 2I2, so it is plus 2I2, and then I plus 2I, that is 3I equal to, and it is minus 1, it will taken right hand side, so it is 1. This is equation number 3. So now we have to simplify these equations to get the value of I, so that we can get the equivalent resistance between A and C, because equivalent resistance between A and C will be voltage applied by current. Voltage applied is 10 volt, we need the current. So we need I. Therefore, we have to eliminate I1 and I2. So using first and second equation, we try to eliminate one of the variables, say I2. So for this is 2I1, and we multiply this equation by 4. So equation will come 4 into 2, 8I1 plus 4I2 minus 4I equal to 0, and second equation is written as it is 3I1 minus 4I2 minus 2I equal to 0, and then on adding we will get this term will be cancelled, and it is 11I1 minus 6I equal to 0. This is the equation number 4. Now we use equation number 2 and 3 to eliminate I2. So for this we multiply this equation number 3 by 2. So equation will become 3I1 minus 4I2 minus 2I equal to 0, and this on multiplication with 2 becomes minus 6I1 plus 4I2 plus 6I equal to 2, and adding this will be cancelled, and it is minus 3I1 plus this is 4I equal to 2. This is the equation number 5. Now in this equation 4 and 5, there are only two variables, and out of these two variables we have to eliminate the variable I1, so that we can get the I. So I1 has the multiplier 11, and here I1 has the multiplier 3. So we multiply this 4 by 3 and this 5 by 11. So we get equation number 4 as 33I1 minus 18I equal to 0, and equation 5 will becomes minus 33I1 plus 44I equal to 22. And now adding these two, this would get cancelled, and it will be simply 26I equal to 22, or I equal to 22 by 26 ampere, or we can say 11 by 13 ampere. So now we put the values of I here. So we get, well, voltage applied is 10 volt and resist current is 11 by 13. So it is 130 by 11 ohm resistance between the A and C.